Hello and welcome back to Calculus 2, section 12.2 on polar coordinates. These are useful for particular shapes and completely not useful for others. And we are going to discover now what these are, how they work, and when are the situations when we should use them and situations when we should avoid them. We're going to start with the polar coordinates point is given as r comma theta, where this would be known as radius and this is known as the angle. Polar coordinates arrive to a point differently than rectangular coordinates. So now I'm going to have one of those like a boxing ring in a blue corner and the red corner, right? Rectangular versus polar. Draw two coordinate systems next to each other. Label both x and y because both of them are x and y. In the left corner half, we are going to have rectangular point. Let's say your point is 3, 5. You will go 3 units in red along the x-axis, and then you would go in blue 5 units up. And you will get to your point 3, 5. You draw x down the x-axis, or negative x if it's negative axis, right? Negative number, and then you go either up for positive y or down for negative y. These are, as you can see, they're working and they are forming the rectangle, so-called rectangular coordinates. You can also go up 5 and over 3, but since we are listing always the x coordinate first, maybe you should go 3 and then go 5. Polar coordinates, 3 and pi over 3, let's say, work differently. What you do first is you draw out the radius 3. That's 3. You draw that along x-axis or negative x-axis depending on whether you have 3 or negative 3. And now what you do is you find where the angle pi over 3 is. Pi over 3 is 60 degrees. So we'll have something like this. Now what you do is you take the red and you swing that like this to hit the blue line, and there is your point 3 pi over 3. That's it. You draw the radius and then you swing the angle. Now, I'm going to draw a diagram here which will have a lot of information. Try to decipher this first and then draw. Pay attention on me drawing these things. This way, the positive r. This way, the negative r. So if you have a positive r, you draw along positive x-axis. If you have a negative r, negative x-axis. This way for positive angles, and this way for negative angles. So all of the stuff you learned before, you know on the number line that you need to draw the right angle, the positive numbers to the right and negative numbers to the left. And you also know from the basic trig course that positive angles in the unit circle go up and the negative angles go down. All right, let's take a look at a point. So you try this one on your own. -4, negative pi over 6. All right, let's take a look at this together. So I'm going to draw -4. 1, 2, 3, 4. So this is where the -4 is. And then I have to go back pi over 6. So negative pi over 6 from this axis is here. So we go back. And this point here is -4 negative pi over 6. Now here is the scary part. Same point as 4, 5 pi over 6. It's the same location on the graph, right? Because I can draw 4 on this side, right? And then go 5 pi over 6 and end up at the same location. Conversion. When you consider this triangle, you can write 3 trigonometric functions plus the Pythagorean theorem. You can write that sine x is equal to y over r, because it's opposite over hypotenuse. From where you can come up with the equation that y is equal r sine x. Not sine x, sine theta. Sine theta. Cosine theta is x over r. from where you can come up with the equation that x is equal to r cosine theta. So now let's use a little bit of common sense over here. Do you see how r and theta are given, and you are coming up with x and a y one at a time? This particular conversion is polar to rectangular. If you use the same triangle to write x squared plus y squared equal to r squared, from there you can get that r is equal to square root of x squared plus y squared. And you can also write the tangent theta as y over x, from where theta is inverse tangent of y over x. This over here is rectangular to polar, because you see that you have both rectangular given, you plug them in and you get polar ones one at a time. So that takes care of that. Now we jump into functions in polar coordinates to see what kind of cool stuff we can get. So let's start by defining the function as r equal function of theta. So we see that theta is domain, r is the range, and f is the function between them. I want you to think of a domain as slices of pizza. Here's the domain where theta is between 0 and pi over 4. You cut the pizza right there, and that's the domain. Domain is going to be very important when you do the integration in the next section, because your integral has to go from, let's say, in this case, 0 to pi over 4. And you are calculating the area of the shaded piece, which is actually the area of one of the large slices of pizza, right? When you take the large pie, it's cut into 8 parts, so that will be one of the 8 parts in the large pie. Unless you go to the children's party when they necessarily make a spaghetti out of pizza. So you take a slice and then you have to take another 17 slices to equal one regular slice, right? You've seen that, right? No. The rectangular system had the two basic equations to be x equals a number and y equal a number, which are horizontal and vertical line. So, rectangular coordinates. If you take a look at the basic equations, here is your x equals 2. And let's say y equals 1. If you haven't noticed that so far, and you should, you see y equals 1 describes the entire line because x will take on all of the values from negative infinity to positive infinity. So x is not mentioned in the equation at all. Same thing here. Y is not mentioned in this equation at all because y will be taking values from negative infinity to positive infinity, while x is always pinned at 2. So these are the simplest equations that you guys have when you are dealing with rectangular coordinates. Now in polar world, you can have r equal a number, or you can have theta equals some theta 0 or whatever, which is the angle. So now what is r equals to a? Well, the same idea like before. You see x is pinned to be 2 and y takes on all of the values. So now if I draw this and I, let's say, extend 2 units, which way and what should I do with this when it's possible to have any value of the 0 to 2 pi? So what should I draw? What would this trace? Circle. Excellent. So this is going to be a circle of radius 2. That's an egg. Okay, it's a circle. And it goes through 2 and goes through x, negative 2, negative 2, 2. Here it is in blood. R equals A is the equation of the circle in polar coordinates. Obviously the r, which is the number, is the radius. And now when you have q equal q0, you pick any angle for q0, it's fine. So let's say that the q0 is this much. So, well, I have to make it solid now because it rotated. This line is a straight line, as you can see, goes through the origin, all right, so let's take a look at the okay, I can feel that I'm missing these. There we go. Perfect. So let's go with the theta equal theta 0 is a linear line through the origin. I'm waiting for it to sink in. X squared plus y squared is equal to 16 versus x equal 4 cosine t, y equal 4 sine t versus r equal to 4. It's like on an AI exam, which one is better? A, B, or C? And then they keep switching until you pass out. You have the equation of the circle in rectangular coordinates. You have equation of the circle, parametric equation set, and then r equals to 4. Which one do you want to integrate? This one, right? It's tomorrow. Hold on. Don't rush. Tomorrow we integrate. Tomorrow we integrate circle in one line, right? Let's see what other cool cases can we come up. We said that r is a function of theta. So what stops us from r equals 4 cosine 2 theta? You know what? 4 theta. 4 cosine 4 theta. Know what you get? You get this. It goes out to 4. You get a flower with 8 petals. Is that a function? Is it going to be pretty if we turn this into xy equation? Let's try it, see what happens. It's going to be disgusting, for the lack of the worst word. R equals 4 cosine 4 theta. What now? Oh, keyboard at the bottom, thank you. I still don't see it. Oh, there it is. Boom, right there. 4 cosine 4 theta gives you 4 times 2, 8 petals. If you are using even numbers, it doubles the amount of petals, and this is how far out it goes. You see that it goes to positive and negative 4, and this 4 inside, because it's even, times 2 gives us 8 petals. If I change that to 5, it will be 5 petals. So odd numbers are as many petals as it's written, even times 2. Here's your 5. So if I change 5, it still goes out to 4. But now we have 5 petals because it is theta. It's 5 theta. 2 will give us 4 petal flower. 10 by 20 petals. They all go out to 4. If I increase that to 5, it becomes larger flower. Now you can, we'll go back to 4, we'll go back to 8 over here, not 8, sorry. Let's go back to 4. No, let's do 2, because I want to add another one over here. But I want this one to be sine. So you can come up with multiple equations, you can come up with multiple shapes. Now I want to frame this into a circle. R equals 4. And then maybe R equals 4.1. Give it a double. You can just keep playing like this and creating whatever all these things, right? Now, obviously, it's not only for flowers and things. There are other, right? You've seen a circle, R equals a number, and you have seen the flower, which is 4 cosine 2 theta. Now, what we can do, we can say R equals 1 plus sine theta, and we get a shape that it's called cardoid. So R equals 1 plus sine theta, and we get, it's in a shape of the heart. It's not a perfect shape of the heart, but hey, it's good. So 1 plus sine theta gives us cardoid. And we saw the flower, we saw the circle, and so on. Here's a cool one. R equals theta. Can you picture this in your head? What would this be? As the theta is growing, radius is growing. What is that? A spiral. Very good. Very good. Your starting radius is 0, theta is 0. And then as radius grows, angle grows, and it's just going to spiral out. So I'm going to kill the cardoid and say R equals theta, and there is your spiral. It spirals out. A lot of cool shapes. Look at these equations. These equations are a joke for the terrifying shapes on the other side, because none of them are functions. You can't integrate any of these shapes in your rectangular world. Well, I'm glad you asked why. How about we just convert one of them and see what they are in rectangular world, and immediately it will be clear. So say you take this cardoid, R equals 1 plus sine theta, and you convert to rectangular to see what it is. Well, R was given as a square root of x squared plus y squared. 1 is 1 plus. Now, if you remember, y was R sine theta, right? So sine theta is y over r. So sine theta is y over r, and r is the square root of x squared plus y squared. So now you multiply both sides by the square root of x squared plus y squared, On the left-hand side, you have x squared plus y squared is equal to the square root of x squared plus y squared, plus these guys will cancel, plus y. Oh, can't see any of that stuff. So if you want to convert r is equal to 1 plus sine squared to rectangular coordinates from polar domain, holy nightmare, right? And look at the equation you got on the bottom. Can you make this into y equals everything else? No, you can't. You can just look at it and cry. There's nothing that can be done there. Here in blood. Cannot solve for y, which means you have to leave it in this implicit form, and then you want a tangent line, implicit differentiation, right? You want an integral, can't be done at all. How hard is to integrate this? You should be able to do this mentally right now in Calc 2 class, right? It's theta minus cosine theta. Come on, a joke, right? Theta minus cosine theta, a joke to integrate. So what this exercise was designed to show is that these two worlds complement each other. They do not compete for problems, because what's beautiful in one world is absolutely disgusting in the other one. Right? Do we see that? Compare the equation on top and equation on the bottom. This equation is completely useless. There's nothing I can do with this thing. Right? Differentiation is annoying. The integral, you can't even think about it. And look at that. Right? And it gives us that heart-shaped. Right? So there are a lot of different situations where this is going to happen. And being able to switch between the systems, as we are going to see tomorrow, in some cases makes the problem much easier to solve. In other cases, it actually makes problem possible to solve. Because if you are supposed to find the area of that heart, well, if you don't know polar integrals, which is tomorrow, you can't do it at all. There's nothing you can do using Calc 1 to find the area of that heart. Because look at the equation. And we do not have integrals for implicit. Right? We have implicit differentiation, and that's annoying too. I'm going to take derivative here. That's cool and easy. I'm not going to take derivative there. That's insane. I mean, you can, but then you like pain and, you know, other things come with it. So those are the few ideas that we explore. Oh, I forgot to do this. Ready? Oh, come on. There we go, much better. Sleepy yet? No? Oh, now it's terrifying, huh? So now you're awake. Okay, fine, you win. In one day, someone to throw the dart at it. But yeah, that's so that's the polar coordinates. We can transform these functions, and as I said, we use polar coordinates to make our life easy in certain situations. So it helps us. It actually helps us. So we'll see the calculus done in polar coordinates. Hopefully you'll do some of the homework exercises today to practice a little bit, to get used to the idea of polar coordinates and to get those conversions of functions and points. So tomorrow, when we are supposed to convert these things, it goes a little bit faster. So till tomorrow.